In this video, we are going to continue our introduction to nuclear magnetic resonance spectroscopy, and we'll be looking at some general information to try to understand the basic principles behind NMR. Now, as we talk about spectroscopy, we are thinking about the interaction of energy with matter. We've looked at infrared spectroscopy, and in this case, the infrared radiation is of the appropriate energy that it will cause bonds to bend or stretch. And looking at an IR spectrum, by observing what is the frequency of the absorption, that tells us what is the type of bond that's present in that molecule. Different types of spectroscopy have different types of energy transitions. So with NMR spectroscopy, now we're looking at energy transitions between nuclear spin states. So the spin state of the atomic nucleus. So some nuclei, not all, but some nuclei behave like tiny magnets. So hydrogen is one example of an element that behaves like a tiny magnet. So like electrons, a hydrogen nucleus has a spin that's called +1/2 or -1/2. So two different possibilities. Now, this can be represented as +1/2, or you can draw an arrow. Here's the energy of the other spin state. We can draw an arrow going the other direction. But the problem is that these spin states are the exact same energy. So we can't get an energy transition. That is true under normal circumstances, that there is no difference in the energies. However, if we take that molecule and we put it in the presence of an applied magnetic field. So B0 refers to an applied magnetic field. And let's say this is going in this direction. Well, now those little magnets are going to have a difference in energy. So this one, where the spin is going up, this one is aligned with the field, so this is low energy, whereas the other spin state is opposing the applied field, and so this one has higher energy. So now there is an imposed energy difference on the nuclear spin states. And so if energy is absorbed, if the right amount of energy is absorbed, then it can cause a transition from low energy to high energy, from high energy falling down to low energy, and this is something that can be observed. Now, what are the differences in terms of the applied magnetic field? Well, once again, if we have no magnetic field, then our two spin states, our up and our down, are the exact same energy. If we have a small applied magnetic field, then maybe this is our low energy and this is our high energy. And so this is what we're looking at in terms of our difference in energy between the different spin states. So let's say, for example, this is a magnet with a strength of 1.41 Tesla. Well, in this case, for a hydrogen nucleus, then that delta E is 60 megahertz. Okay, so that's the size of this energy gap. Now for reference, 60 megahertz, this is in the radio waves. Now in contrast, if we have a larger applied magnetic field, let's say now we're looking at 4.7 Tesla. Here's our low energy spin state that is aligned with the applied field. Now here is our high energy spin state that opposes the applied field. And now we have a much bigger delta E. So here, for a hydrogen nucleus, the delta E, for example, is 200 megahertz. So a higher applied magnetic field requires a higher energy to be applied, but it can also give a lot more information. Now, in an applied external magnetic field, there is a delta E. There's an energy difference for the plus and minus nuclear spin states. And the size of that energy gap depends on the strength of the magnetic field. But within a given magnetic field, well, are all of the nuclei going to absorb the same? So we're going to just focus on hydrogen nuclei. Are all of the hydrogens going to absorb the same amount of energy? If so, then this method is not very helpful. Obviously, there's a difference, or else I wouldn't be telling you about this technique. So all of the hydrogens in a molecule in the same applied field do not absorb the exact same amount of energy because the hydrogens are affected by other atoms, especially if we have another atom that is very electronegative. Hydrogens can be affected by bonds, and hydrogens can be affected by the electrons around them. In other words, hydrogens within the same molecule will feel a different environment. We think of it as a different electronic environment. So electrons can shield the hydrogen nucleus, right? The electrons shield the hydrogens so that they don't feel the full applied magnetic field. If we have a hydrogen connected to a carbon, let's say this is the applied field, and that leads to this particular delta E. However, because of shielding by electrons, then what the hydrogen feels is called a B effective, and that gives rise to a slightly smaller delta E. All right, so the applied field would generate this energy difference, but the field that is actually felt by the hydrogen, because of how it's affected by the electrons, that leads to a slightly smaller energy gap. Because of primarily electron shielding, a hydrogen feels a lower magnetic field, so lower than the applied field, and that gives a smaller energy difference. Now, within the same molecule, different hydrogens are going to be shielded or deshielded differently. So each set of hydrogens could feel a different effective magnetic field, leading to different delta E's. And therefore, even within the same applied magnetic field, different hydrogens in the same molecule will absorb at different energies. Before we move forward, I wanted to highlight something that we use in the terminology. So on an earlier slide, I had written this, but I called it proton NMR. So this is the symbol for the hydrogen nucleus. We are talking about nuclear spin states in NMR spectroscopy, so we're focusing on the nucleus. Now, the nucleus of hydrogen 1 contains 1 proton and 0 neutrons. So the H1 nucleus is a proton. And so this is why we will often write it as H1, but we will say it as proton NMR. So for NMR spectroscopy, we insert a sample into a magnetic field to impose an energy difference between the nuclear spin states. Then we apply radio waves and we monitor for absorption. Now, the differences in absorption is going to depend on the environment and how much of the applied field a particular set of hydrogens actually feels. So let's think of this from the perspective then of the shielding by the electrons. How much do electrons shield the hydrogens? Well, it mostly depends on electronegativity. There are other factors, but electronegativity is going to cover a lot of what we're going to observe. So in our first example, we have a hydrogen connected to an sp3 hybridized carbon that's connected to another sp3 hybridized carbon. The electronegativity difference between hydrogen and carbon, we can pretty much ignore it. So in this case, this hydrogen is very much shielded by the electrons in these bonds. Because these electrons are shielded, then they are going to feel a lower B effective, which means there is a smaller delta E, and so a smaller frequency of absorption. If we have a hydrogen connected to a carbon that's connected to an oxygen, well, because the oxygen is much more electronegative than the carbon or the hydrogen, this is going to be pulling away electron density, which is going to be de-shielding this hydrogen. So it'll feel a higher B effective. Here we've got the hydrogen connected directly to an oxygen, and so this is the most de-shielded. All right, so the electrons are not shielding the hydrogen nucleus, so that the B effective is almost the same, we can think of it, as the applied magnetic field. So it means it's feeling a really big magnetic field, which leads to the largest of the delta E and the largest frequency. All right, now considering these three different types of hydrogens, here we have the smallest energy gap, medium, and the largest energy gap. So what does that look like? Well, unfortunately, the frequency of that energy gap actually depends on the magnetic field. So if we were using a 60 megahertz instrument, then this difference would be 60 hertz. This one would be 210, and this would be 720. So that's great. We can see a significant difference between these three types of hydrogens. But the problem comes in because if instead of the 60 megahertz, if we use, for example, a 500 megahertz instrument, well, this hydrogen would absorb at 500 hertz, this one at 1750, and this one at 6000 hertz. So the good news is we can see a difference between the different types of hydrogens. The bad news is there's also a difference depending on the magnetic field strength. So if we're using a different instrument, we're going to have a whole different set of numbers. All right, so that's kind of a problem. But we can address the problem rather than using a range of frequencies in hertz, we can instead compare it as parts per million. So looking at this particular frequency, this is 60 hertz out of 60 megahertz. So that is 60 million hertz. And then we multiply that by 10 to the 6th, because 10 to the 6th is what then gives us ppm. And that is then equal to 1 ppm. So this hydrogen on a 60 megahertz instrument will have an energy gap of 60 hertz, so it'll absorb energy at 60 hertz, and that corresponds to 1 ppm. Now for the 500 hertz, we do 500 hertz divided by the 500 megahertz, and then times 10 to the 6th so that we get to ppm. And guess what? This is also 1 ppm. So we don't use hertz to compare between different instruments. We use ppm. You're not going to have to do this much, but I do want you to have an idea of how to do this. So try out the math, and what you should find here, we have 210 divided by 60 million times 10 to the 6th, and this gives 3.5 ppm. This one is 1750 over 500 million times 10 to the 6th, and that's also 3.5. And for these, you should get a value of 12 ppm. So ppm, this is what is symbolized as delta. So we talk about the delta, or the chemical shift, is given in ppm, parts per million. So fortunately, we don't have to learn many sets of values. We just need to learn the ppm value where a particular type of hydrogen absorbs on any type of NMR instrument. Now, as we think about the basic operating principles, I wanted to start with the continuous wave NMR. This was the original type of instrument, and this had a constant radio frequency, and then the applied field was varied. This was a very slow technique. It was limited to a single scan because at a particular radio frequency, the instrument would have to scan through the variation of the magnetic field, and it could only do it once. It was limited to only hydrogen nuclei. It couldn't be used for others. So this method is not used anymore, but it did give us particular terminology, such as talking about upfield and downfield. I tend to avoid using these terms, and in fact, I always have to remind myself of rolled. To the right of the spectrum is upfield, on the left side of the spectrum is downfield. Depending on the way you learned about this, you might be most comfortable with the upfield, downfield, but this is where it comes from, is an obsolete type of instrument. What's used now is called pulsed Fourier transform NMR. So with FT NMR, a superconducting magnet is used. So rather than the 60 megahertz, you could use a 300, a 400, 500, there's 900s, there's gigahertz instruments, and even bigger. These are cooled by liquid nitrogen and liquid helium, and in some cases they also have to be in specially designed rooms because the magnetic field is so strong. Now with the pulsed FT NMR, this uses a pulse of energy. So it is a wide range of frequencies so that all of the nuclei are excited at the same time. Right? So we talked about having that energy gap where if this is our applied field, we have our low energy nuclei and our high energy nuclei. By giving a big pulse of energy, then all of these are excited up to the excited state, and then the nuclei are going to relax back down to the ground state. Now, the rate of relaxation depends on the electronic environment. What does the spectrometer see? All right, when all of the nuclei are excited at one time, then they all have the same orientation in a magnetic field. In other words, this generates an electric current. Then as the nuclei relax, that electrical signal is going to decrease. So when all of the nuclei are excited, it generates a large electrical signal. And then as the nuclei relax back down, then this signal is going to get smaller and smaller until all of the nuclei have relaxed. So this is called the FID, the free induction decay. And even though it just looks like a bunch of scribbles, It's actually made up of a bunch of different frequencies. And now these can undergo Fourier transform, and then it converts these squiggles into different types of squiggles. So it gives you specific peaks. So the pulsed FT NMR is a lot more complicated. It's not that continuous wave NMR is intuitively obvious, but it is much more intuitive than pulsed FT NMR. Why do we need this if it is so complicated? Well, there are many advantages to FT NMR. So one of them is that there is better resolution. Because you can use a higher magnetic field strength, that is going to lead to a greater separation. So let's say at a low magnetic field strength, we're going to get a signal like this and then another signal like this, so that overall what we see is just kind of this lump. But at higher magnetic field, we get the signal centered at the same place, but we're going to see separation between them, so more detail. And that's what we have over here. This signal is at the same ppm, this is the same, this is the same, and this is the same, but we can see much more detail. Here, these signals are overlapped on top of each other, whereas here, these signals have been separated. And so by going to a higher field strength, we can get more detail in our spectra. Another advantage of FTNMR is that it is much faster than the continuous wave. The continuous wave instrument would require several minutes to do a single sweep, whereas with pulse FTNMR, it only takes a few seconds, which means in the same amount of time, you can do many, many scans. And so it's okay if you have less sample. In addition, you can use multiple pulses. Now, if you have multiple pulses in a short amount of time, that helps to cancel background noise. If you have one pulse, then maybe it is going to lead to bumps. Maybe some of these are real, maybe some of them are just noise, right? It's just some glitch. But if you have multiple pulses and they are averaged together, then there's going to be a better distinction between what's just noise and what is a real signal. So the signal to noise ratio is much, much better when you use multiple pulses. And then finally, another big advantage of the FT NMR is that you can use more nuclei. We are not limited to just hydrogens, okay? We're not limited to just H1. We can also use C13, we can do fluorine 19, we can do P31, and many, many other nuclei are possible. NMR has been applied to determining protein structure. These are very, very complicated molecules, and yet NMR has been used to learn a lot of information about proteins and other biological molecules. So FT-NMR is much more complicated. If you take additional courses in instrumentation and spectroscopy, you will get to learn so much more about what's happening in NMR. But I just wanted you to be aware of kind of the background information. Knowing where this all comes from, we are next going to focus on, okay, what do we do with this information, right? What is the information that we get out of it? And then how do we interpret that to determine molecular structure?